Okay, so we're on packet number 11, and we are looking at expanding our knowledge of logs and how to relate logs and exponentials to solve equations. So we are going to actually talk about some of the log rules, which are meant to help you manipulate even further. So let's look at the product rule. Basically, this is it. If you have the log of something or the natural log of something, and what it is being taken the log of, in this case, it's log base A of xy. If you are multiplying what's inside of those parentheses, you can rewrite that log as a sum of two logs. So the best way to really get to know this rule is to try it. Here's your first example, number 1. If you have log base 3 of 2xyz, which are related by multiplying 2 times x times y times z, I can write this as 4 terms. The first term being log base 3 of 2. Second one is log base 3 of x. Third one is log base 3 of y. And the last one is log base 3 of z. We kind of call that expanding, right? Because we took something that was a single log and we expanded it into 4 terms. If we did the number 2, this one's a little bit less of an expansion, but we have the natural log of 2 plus the natural log of x. It's supposed to be squared. We went subscript instead of superscript. And then the last one, log base 4 of 9 combined with log base 4 of A, log base 4 of B, plus log base 4 of C squared. If you understand how to expand, then you should also be able to do it backwards. So if you were given an expanded log, then you should be able to recognize whether or not you can combine it and write it as a single log. All of the terms have to have the same base in order for you to be able to do that. Let's look at number 4. So I'm doing log base 3, and then I see that I have 4 factors in here, 14 x y to the 5th z. So there is written as a condensed logarithm. Number 5, if I put this in the parentheses, this is like log of 6 times 4x plus 2. If I were to work that out, it would look like log of 24x plus 12. The last one, natural log of 9xy to the 5th power. Okay, so we're on the next page. We have the quotient rule. The quotient rule states that when you take the log base whatever of something, if that something is a quotient, then you can write that as terms that are being subtracted. So it's like the top minus the bottom. So if I was going to write the first one using this rule, it would look like this. It would be log base 3 of 6. Now on top we have terms that are multiplied, so I'm going to have to make sure that I'm dealing with this top using the product rule, plus log base 3 of x plus log base 3 of y, and then when I want to address the denominator, I have to subtract log base 3 of z. So anytime I'm looking at this, this tells me that we are dealing with a quotient. Looking at number 2, we have natural log of 3 plus natural log of a squared plus natural log of b minus natural log of 2 plus natural log of c. For number 3, log base 7 of 17 plus log base 7 of n to the 4th minus log base 7 of m to the 5th. Now that you have 2 rules under your belt, when you are asked to write something as a single log, you might have to look for more than one thing. We're not just looking now to see what's going on here with each of these terms, but now these really, really mean something. So whenever I see that minus sign, that means I have to draw a fraction bar and go to the bottom. So we have here log, and then I'm going to open up and say on top we have 2x, fraction bar on bottom, 7z squared. My z looks not very z-like. Next one, natural log. Open your parentheses, 5ab. We have a minus sign, so that means I need to put a division symbol, 7c squared. And then the third one here, log base 6. Open my parentheses, 3x goes on top, 5y goes on bottom. Okay, next page. The power rule. So the power rule is probably one of the most interesting of all of them. Basically, if you have a log with a base and your number that is next to the base has its own exponent and you rewrite it, you can actually take that exponent and you can put it in the front of your log. Basically what this is now it's like n log a to the x. So I'll show you what that looks like. Maybe I will give you an example. If you had log of 2 of x cubed, I can write this as 3 times log of 2 base 2 of x. So I can pull that 3 down and put it out front. So if I were to write these next ones, I'm expanding and I'm using the power rule. This would look like log base 3 of 4 plus 3 log base 3 of x plus 5 log base 3 of y. So notice that the 3 and the 5 came out up front. You have to do a little bit of forecasting and looking ahead to see what's going to happen with that. The next one, we have log of 2 plus the log of x plus 2 times the log of y minus the log of 6 plus 5 log of z. Usually when I show people this, they're always surprised at how easy it is or how much of a simple concept it is, and it looks so complicated when they see it completed. The next one, I have the natural log of 3 plus 7 times the natural log of a minus the natural log of 14 plus 3 natural log of b plus the natural log of c. And then the next part of this, you are asked to condense something that's written. So this first one, I noticed they're all logs. So I'm going to say log of 3x squared over z to the 5th. The next one, log base 4 of 9 y to the 6th z squared over 4. And then the last one here, I have the natural log of x to the 5th over y squared z to the 5th. Okay, so after going over some of those, I want to show you how they may or may not become part of solving logarithmic equations. Remember that logs and exponents are sisters. So if you're at a place in an equation where your x or whatever variable you're using is buried somewhere in a place where you usually can't get to it, then your last hope, I don't even know what I'm trying to say, your last resort is to change it to the other form. So if it starts off as a log, change it to an exponential. And if it starts off as an exponential, maybe change it to a log. For the very first one, we have the natural log of x equals -3. I'm going to change this to exponential form. Remember, the base here is going to be e. So I actually say e raised to the power of -3 equals x. E to the -3 is actually a number. I'm just going to put it in Desmos. I get 0.0498. Looking at the next one. There really isn't anything we can do here to simplify, so we are going to change this to exponential form. The base here is 10, so I raise 10 up. These two get switched. 10 to the second power is 3x minus 2. 100 is 3x minus 2. If I add 2 to both sides and then divide both sides by 3, x is going to be 334. Cool. Let's look at the next two. Let's look at this fun one. I'm going to move this over here. So this is now equal to 0. I can condense this into one log by saying log of 2 times 3x minus 4 over x squared. And I can also change this to log form, or exponential form, I'm sorry, by raising, so here's my base here. So 10 raised to the power of 0 equals 2 times 3x minus 4 over x squared. Anything raised to the power of 0 is 1. 1 equals 6x minus 8 over x squared. I can multiply both sides by x squared to get it out from under where it is. So now I have x squared equals 6x minus 8. I'm going to put all of my stuff over to the left. Subtract 6x, add 8. So now I have x squared minus 6x plus 8 equals 0. And I can factor it in. I can find my solutions. For -4, -2. So my two solutions are going to be +4 and +2. Yeah, you can get two solutions, so that's kind of cool. Let's do that. Okay, let's try the next one. These ones are really, really challenging. I'm not going to take that away from anybody. We're going to do the same thing again. We're going to move this one the left side over. So we have the log of x plus the log of x minus 1 minus the log of 4x equals 0. Write this as a single log. X times x minus 1 over 4x equals 0. Change this to exponential form by taking the base and blowing it up big, switching the left and the right. I probably just screwed myself with room. X squared minus x over 4x. Remember also now this thing here is now 1. I can say 10 to the 0 power is 1. So I'm going to put that there. And then I'm going to multiply both sides by 4x to get that out from underneath. So now I have 4x equals x squared minus x, and I have to subtract 4x from both sides to set this equal to 0. So where we're at right now, I'm going to have to do a little zooming, is we are at 0 equals x squared minus 5x. And I can factor this by pulling an x out. And so it gives me two solutions. One of them is 0. One of them is 5. At any time, if you're ever doubtful of your answers, you can always go into Desmos and put this into the left, but replace all the x's with a 0. Put this one in another one, and then replace x with 0. See if you are getting something that makes sense. Actually, no. You can put these in, and you can graph them and see where they intersect, and I guarantee it's where x is 0 and where x is 5. Okay, let's keep it going here. Looking at this next fun one. Log base 3 of x plus 25 over x minus 1 equals 3. 3 raised to the power of 3 equals x plus 25 over x minus 1. I would multiply both sides by x minus 1. But first, I'm going to change 3 cubed to 27. Multiply both sides by the denominator. Cross, cross. I have 27x minus 27 equals x plus 25. Moving my x's to one side and moving my numbers to another side, I have 26x is equal to 52, and if I divide both sides by 26, x is equal to 2. Mind blown. Okay. Number 6. I'm going to condense this. The log base 9 of x minus 5 times x plus 3 equals 1. Log base 9 of x squared plus 3x minus 5x minus 15 equals 1. And then I can go ahead and combine these two inner terms, make those two inner terms negative 2x. And then I'm going to go ahead and change this to exponential form. 9 to the power of 1 equals this. Subtract 9 from both sides. And then I'm going to go ahead and factor two numbers that can multiply, give negative 24, but add to give negative 2. 1, 24, 2, 12, 3, 8, 4, 6. It's going to be 4 and 6. X is negative 6, and x is, we have the positive 4. And then my solutions would be positive 6 and negative 4. In this case, we're not dealing with complex numbers. They're looking for real solutions. So we're going to reject this one. We're just going to use this one right here. Okay. No complexities, I guess, right now. Let's look at the next one. Okay. Log of x times x minus 3 equals 1. 10 to the first power equals x times x minus 3. 10 to the first power equals x squared minus 3x. Take 10 away from both sides. Two numbers that multiply to get 10, negative 10, and combine to get negative 3. It would have to be 5 and 2, negative 5, positive 2. So my solutions here are positive 5 and negative 2, and negative 2 gets rejected because it's negative. So we don't accept it. Just 5. Another one. Log base 2 of x minus 2 times x plus 1 equals 2. So that's log base 2 of x squared minus x minus 2. Change this to exponential form. 2 squared equals x squared minus x minus 2. 2 squared is 4. Take 4 away from both sides. Two numbers you can multiply to get negative 6, or add to get negative 1. Has to be 3 and 2. Negative 3, positive 2. So my solutions are positive 3 and negative 2. And negative 2 got rejected. So it's just positive 3. It's the ugliest 3 I've ever seen. I don't know if we could just work on this 3 and give her some beauty. Okay. Let's look at the next page. Okay, we are looking at solving equations. These equations are starting off as exponential equations. They look like they would be easier, but looks are so deceiving. So let's just dive right in. Anytime you're solving an exponential equation, you really want to try to get the power alone as much as you can before you start making rash decisions. So I'm going to add 2 to both sides. I have 3 raised to x power equals 14. I need to get x out of the exponent spot, and the only logical thing I can do here really is to change this to log form. If I did, it would be log base 3 of 14 equals x, and it becomes something that I have to put in Desmos. I'm going to do that as I'm sitting here. Log base 3 of 14 gives me an approximate answer of 2.402. Next one. Next one's already in the simplest form, so we're just going to have to go right to putting this in log form. So this is like log base 3 of 2 equals 1 minus x. And I can subtract x from both sides, or subtract 1 from both sides. And then I need to make this like positive, so I'm just going to divide both sides by -1. And this is what I put into Desmos. Let's see, log base 3 of 2 minus 1, set of parentheses around the whole thing. On the bottom is -1. So that gives me an approximate answer of 0.369. Let's go to number 3. Okay, so look at the situation here. We've got an exponential on both sides. We're going to have to just take the log of both sides because there's the only way we can get something out of the exponential spot. But we can manipulate things a little bit also. If you recall that rule that if you have a log that has a base that is equal to whatever the log is being taken of, that this would be equal to 1. So knowing that, I'm going to go ahead and I'm going to take the log of both sides, but I'm actually going to take the log base 4 of both sides because I can do whatever I want as long as I do it both sides. So that's going to look like this. X comes out front. Log base 4 of 4 equals x plus 1 comes out front. Log base 4 of 5. Now, this right here we know is equal to 1. So that can be gone away. Now we have x times x plus 1 equals log base 4 of 5. Remember that this is just a number right here. So like if I wanted to, I could distribute that number. Log base 4 of 5 times x plus log base 4 of 5. I distributed this number over here. I'm going to move this to the left side too because I like to have my x's on the same side. So now I have, here we go, I have x minus log base 4 of 5x equal log base 4 of 5. I'm going to factor my x out of this. So it's going to be x times 1 minus log base 4 of 5. It's a lot of manipulating, I know. Okay, x is now isolated. We did some crazy stuff. I can now get x alone if I divide both sides by 1 minus log base 4 of 5. I'm going to put that in my calculator. See what I get. Log base 4 of 5 over 1 minus log base 4 of 5 gives me an approximate answer of -7.213. Oh man, look at all that fun. Of course I'm going to give us another one like it because why wouldn't I? Let's look at the next one. Okay, how can we manipulate the situation? We can take the log base 6 of both sides. That'd be kind of cool. Let's try this. 1 minus x log base 6 of 6 equals x log base 6 of 10. So now we have 1 minus x over here because this canceled each other out. If I were to get myself in a situation again where all my x's were on one side, I could be in a position where I could factor out an x. So if I wrote this in factored form, it would look like x times log base 6 of 10 plus 1. And that would allow me to get x by itself. Cancel, cancel. This is what goes into Desmos. 1 over 1 plus log base 6 of 10. The approximate answer is 0.438. Holy henna. Pretty cool. I love math. I'm the only one probably, but that's okay. Let's look at number 5. Here we go. We can either take the log base 3 of both sides or the log base 2 of both sides. Let's see. So let's take the log base 3 of both sides. And I can move my 2x plus 1 up front. Log base 3 of 3 equals, and we have our x minus 2 up front, log base 3 of 2. This is canceled now. 2x plus 1 equals x minus 2 times the log base 3 of 2. And this is just a number, right? So I can do this thing where I can put I can distribute and then move my x's to one side, move my numbers to the other side, and then try to factor an x out and get it alone. So if I were to distribute this here, I would have 2x plus 1 equals log base 3 of 2x minus 2 log base 3 of 2. So I'm going to get my numbers over here, and I'm going to get my x's over to the left. So that I have 2x minus log base 3 of 2x equal to negative 2 log base 3 of 2 minus 1. And then I'm going to factor out an x. And if I do that, this is going to look like 2 minus log base 3 of 2. And now all I have to do is divide both sides to get x alone. And this whole crazy thing is going into Desmos. So let's do that. And the top is negative 2 log base 3 of 2 minus 1. And then that whole thing is going over 2 minus log base 3 of 2. And that gives me an approximate answer of negative 1.652. Beautiful. You want to check this? Put this in the calculator on the first row, put this in the second row, and then look at both of those graphs and see where x collides. And I bet you it's here. I bet you. I bet you Thanksgiving dishes. Let's look at number 6. Anytime I see something like this, my first instinct is to multiply both sides by the denominator. So I'm going to do that. That's going to cross off this one and come over here. So we have 10 equals 2 plus 2e to the negative x distributed. Subtract 2 from both sides. So 8 equals 2e to the negative x. divide by 2. So now I have 4 equals e to the negative x. Take the natural log of both sides. Natural log of 4 equals negative x natural log of e. Whenever you take the natural log of e, that is equal to 1. So that pretty much cancels that out. And now I just need to make x positive. So in my calculator, I'm going to say negative natural log of 4. Negative natural log of 4. It is approximately negative 1.386. That one was really nice to us compared to the other ones. Let's look at the next one. This is a really interesting situation. So we have things on both sides that make this kind of challenging. So I think I'm going to propose that we do this a little bit differently in the sense that I want you to look at this first term as if this is basically 5 to the x power squared, because that's really what it is. If I was going to simplify that, I would multiply the exponents, right? And even to make this easier, I'm actually going to use substitution for a moment to get through our equation, and then you'll see what I mean. So I'm going to let t equal 5 raised to the power of x. And that way I can write this as t squared minus t minus 12 equals 0. If I was going to solve for t here, t would be t minus 4t plus 3. And then my two solutions for t would be positive 4 and negative 3. So how does this help us? Well, basically this, if t is equal to 5 raised to the power of x, and t is 4 or negative 3, I could say now I am going to solve these. So now this has made life a lot easier because I can go ahead and take the log of both sides. Well, not the log of both sides, but I can change these to the log form. Log base 5 of 4 is one of the possible values for x, and then I have log base 5 of negative 3 as one of the possible values of x. I say possible values because there's always that chance that I put these in the calculator and they come out as non-real numbers, and then we would reject what we have. But the first one gave me a value of 0.861, and then the second one gave me a value of undefined. I had a feeling, so this one is not real. We're going to throw it out, and we have one solution. Pretty crazy. I would be remiss if I didn't just do the same thing twice so that you could like practice it. Again, why don't we let E, oh my god, undo. Let's let t equal e raised to the power of x, so that we have substitution here. We can write this as t squared minus 2t equals 15, which I would rewrite this with the whole thing equal to 0 so that I can factor it. T minus 5t plus 3. So t can be positive 5, t can be negative 3, and then we put ourselves in this position now where we say, okay, if t is e to the power of x, then we need to say e to the power of x equals 5, and then e to the power of x equals negative 3, and then we'll change this to log form. I'm going underneath our little decoration here. Natural log of e of 5 equals x. Remember that e is the base that's there, so really x is natural log of 5. And then we have natural log base e of negative 3 equals x. Again, I'm assuming that the way this turns out, we have one answer that is real and one that is not real. The natural log of 5 is 1.609. The natural log of negative 3, lo and behold, is not real, so we throw that one out. And we have our one solution. Find the inverse of each of the following functions. Well, we've got lots of skills now. We know what we were doing before. Let's write this with y. This was what we were doing before. First, we would write it with y instead of function notation. Then we switch the x and the y. And then we have to solve for y. So I'm going to start by adding 5 to both sides. So x plus 5 equals log base 2 of y minus 3. And we have really nowhere to go except to put this in exponential form. So if we did, that would make the 2 big, the x plus 5 comes up here, and the y minus 3 comes here. And then remember that the whole point here is to get y alone, so I'm adding 3 to both sides, and what that gives me is y equals 2 raised to the power of x plus 5 plus 3 is our inverse. It looks weird, but it is a thing. It is an inverse function. We were able to get y alone. Wow. Let's look at the next one. I'm going to write it with y. Y equals negative 2 log 2 x minus 1 plus 2, and then we're switching them. X equals negative 2 log of 2 y minus 1 plus 2. Subtract 2 from both sides. X minus 2 equals all of this fun going on here. I would also divide both sides by negative 2. There we go. And then if I were to write this in exponential form, this 2 becomes big, and then this side right here switches with this side. So this is 2 raised to the power of x minus 2 over negative 2 equals y minus 1, and I add 1 to both sides. So my inverse function is this. 2 raised to the power of x minus 2 over 2 plus 1. Wow. Where are we at here? Y equals 2 to the power of x minus 3. X equals 2 to the power of y minus 3. Add 3 to both sides. X plus 3 equals 2 raised to the power of y. We're going to have to use logs. We got to change this to log form. Log of base 2 of x plus 3 equals y. So my inverse here is log base 2 of x plus 3. Last one for this anyway. Y equals negative 5 times e to the negative x plus 2. I'm going to rewrite this, flip-flopping my x's and y's. I'm going to subtract 2 from both sides. I'm going to divide both sides by negative 5. So now I have e to the negative y equals x minus 2 over negative 5. Change this to log form. Natural log of x minus 2 over negative 5 equals negative y. And I can multiply both sides by a negative, which ended up making this a positive y and this a negative. And so our inverse function is negative natural log, open up, x minus 2 over negative 5. You can always graph these and see if they reflect over the line y equals x, because that's what we do, right? Only a few more, I promise. Let's look here and see what we got. $15,000 is invested in an account that yields 5% interest per year. After how many years will the account be worth $91,221.04 if the interest is compounded yearly? We have our interest formula. It looks like this. Y equals the starting amount times 1 plus the rate over the number of times compounded raised to the power of number of times compounded times time. So we invest $15,000 and we are ending up with this much. So actually going to plug in the 91,221.04 in for y. 15,000 is in the starting amount. 1 plus, they say the rate was 5%, and it was compounded yearly, so that is over 1. Raise the power of 1 times time. So really what we're looking for is how much time. We're looking for t. Okay. We can divide both sides by 1,500. 15,000. 15,000. So now we have this number, whatever this number is. So I've not even put it in the calculator yet. And this is equal to 1 plus 1.05 raised to the power of t, if you simplify. Really, all I need to do here is change this to log form. That will make my life much easier. So I'm going to do, yeah. I hate how this looks because it makes me confused. I have to have it so that that is in the left and this is in the right. Okay. Log of 1.05 of 91,221.04 over 15,000 equals t. And so I put that beautiful thing in the calculator. Log base 1.05 91,221.04 over 15,000 gives me 36.99999 years, approximately 37 years. So basically I would have had to put that in the bank when I was 7 and have 15 grand when I was 7. I didn't have 15 grand when I'm 44. Okay, let's look at number 6. 8 grand is invested in an account that yields 6% interest per year. After how many years will the account be worth? 13,709. God. Interest compounded monthly. We want to end up with this. We started with this. 6% interest compounded monthly. Raise the power of months times time. Divide both sides by 8 grand. This is 1.005 raise the power of 12t. Craziness. Before I start whipping out logs and such, well, I guess I could. It just depends on how you decide to do it, but all right, I'm gonna do the thing where I switch their sides because I have to. That goes over there. Log of base 1.005 of 13,709.60 over 8,000 equals 12t, and then I can divide both sides by 12. Whew. And that ugly thing is what's going in my calculator, and it's very possible that that can be easily put in Desmos. Log base 1.005 of 13709.6 divided by 8,000, and then that whole thing divided by 12. Oh, it's almost exact. 9 years. 9 years. Let's go to the next page. I know you're sad that this is the last page, I can tell. Starting at the age of 40, an average man loses 5% of his hair every year. What age would an average man expect to have half of his hair? He starts off with 100% of his hair, right? So let's just say that this 100 is going to represent the percent of hair that he started off with, and 50% is what we're going to expect him to leave off with. And we're going to say that he starts off losing, so we're going to say and then we're going to put this to the year, so we'll say T, right? So basically, we haven't really looked at it this way, but this is decay, and 0.95 means a 5% loss. So I'm going to divide both sides by 100. That gives me half equals 0.95t, and then I'm going to use logs. So log base 0.95 of 0.5 equals t. And I'm going to put that in my calculator, and then I will tell you the dismal outcome. Log base 0.95 of 0.5, 13 and a half years. Bald is beautiful, though. I'm trying to think of how many bald people we got in our room. I can't. I'm really bad at that. Okay, a bacterial culture starts with 1,000 bacteria, and the number doubles every 40 minutes. Find the formula for the number of bacteria at time t. Remember that the way that we do this is we have what we start off with times our growth or decay factor. They are saying it doubles, so this is 2, and then it says it doubles every 40 minutes. So if you think about that, we could kind of do this thing where we are putting this to time, and time is worth minutes or time is worth hours. So how many 40 minutes has happened in an hour? That is like 1.5. So I can say that if I went a whole hour, that it would have doubled once, and then it got halfway to the next doubling, and so there is our thing, right? There's multiple events happening in 1 hour. Find the number of bacteria after 1 hour. So we go ahead and we put this and we plug in 1 hour into here. Put it in my calculator. 1,000 times 2 raised to the power of 1.5. That would be 282, oop, goodness gracious, we'll look at this awful, 2828.43 bacteria. After how many minutes will there be 50,000 bacteria? Okay, 50,000 minutes, equals 1,000 times 2 raised to the power of okay, so they're saying minutes. So why don't we do this thing where we put this formula in the terms of minutes? So we'll say x over 40, because remember that every 40 minutes happens to be a doubling. So I changed my formula a little bit to make it geared towards minutes and not hours. Okay, so now I'm going to divide both sides by 1,000. And that's going to give me 50. I can raise both of these to the power of 40. Hopefully you're seeing why I'm doing that. It allows me to cancel out the 40, so I have 50 raised to the power of 40 equals 2 to the x, and then I can go ahead and change this to log form, which make my life a lot easier. So this would be like log base 2 of 50 to the power of 40 equals x. I'm going to put that in my calculator. Log base 2 of 50 raised to the power of 40. That gives me 225.75 minutes. Just like with all of our other equations, you could have taken a different journey and ended up at the same destination. So that is the end of these notes. I know you're probably super stoked because they were really long. If you have questions, please post them on Schoology. Remember, exam 3 is on there also, and that is due Tuesday. Hope everybody has a great Thanksgiving. Take care.